right, welcome back. Last time we started out with the property of face boundaries in plane graphs, namely observing that they generate the cycle space. And then we proved the same more generally for graphs that are not necessarily planar. Now, of course, we can't talk about the face boundaries of non-planar graphs, so we had to come up with some other description of these same cycles, namely the face boundaries of plane graphs, a description that divorces the notion from topology and from their role they play in planar graphs. And this description was that they are what we call the peripheral cycles, the non-separating induced cycles in the given graph. And then we showed that if the graph is three-connected, then these always generate the cycle space. So that was a theorem of Tutte that we proved last time. And I would like to look again at face boundaries today and ask more ambitiously, well, they seem to be a sort of rather special bunch of cycles in plane graphs, so maybe they play another role and we can use them a little more. And the ambitious goal is to say, well, maybe we can characterize planarity, the whole property of being planar, of having a drawing, in terms of how these face boundaries in a plane graph hang together. So obviously, in order to come up with the characterization of planarity in terms of some collection of cycles, we'll have to refer to these cycles in non-planar terms, but we can already do that. So we can already refer to them as peripheral cycles, non-separating induced cycles. So we're hunting today for a condition that tells us a graph is planar if and only if the non-separating induced cycles, the peripheral cycles, behave in this or that way. Well, what might this or that way be? Well, we'll look at the face boundaries again in plane graphs. And how do they behave? How do they hang together? Well, they hang together, literally, and cover the whole graph. They cover all the cycles in the sense that they generate the cycle space even. So that's one thing we have already observed. And another thing we can observe is that they sort of hang together only, well, loosely, right? They're spread out over the graph in the sense that every edge lies on at most two face boundaries, right? If you take an arbitrary collection of cycles in some graph, maybe one edge is in 17 of them, or in all of them. Okay, so the face boundaries hang together, cover all the cycles in the sense that they generate the cycle space, and they're spread out over the graph in the sense that every edge lies in at most two of them. At most, or exactly? Remember graph theory 1? Yeah? That's right. So if the graph is two connected, every edge does in fact lie on two face boundaries. If the graph is not two connected, but it may be connected if you look at an edge that's a bridge, then left and right is the same face. Okay, so here's the theorem we're going to prove. It says that a graph is planar if and only if the cycle space has a basis that we call sparse. Sparse is used in lots of ways in graph theory. This is a particular use of the word, not the most common use, but let's say that a family, or no, a set of elements of the edge space, so a set of edge sets is sparse if every given edge lies in at most two of them. right? In particular, a generating set for the cycle space, or even a basis, is a sparse basis if it is a basis, and every edge lies in at most two of its elements. And MacLane's theorem says that if and only if the cycle space has such a sparse basis, is the graph planar. Okay, right, and one direction is clear. If the graph is planar, then the face boundaries do exactly that, right? So the face boundaries, well, they don't form a basis, but they contain a basis. They generate the cycle space, and you can drop one of them, and then they form a basis if the graph is connected. And then we do have a sparse basis if the graph is planar, starting from any drawing. So we want to show the converse. What do we have to show? Well, we have to show that if we have a sparse basis in the cycle space of any given graph, then the graph is planar. And the way we're going to do that is to show that it satisfies the Kuratowski criterion, that it doesn't contain a subdivided K5 or K33. And how are we going to do that? Well, we're assuming there's a sparse basis for the cycle space. And then the plan is to show that, well, if the graph is not planar, it contains the subdivided K5 or K33 somewhere inside. And the idea is to show that we can shed edges and maintain the property of having a sparse basis for the cycle space until we're all the way down to that subdivided K5 or K33. And if we succeed in doing that, then the subdivided K5 or K33 will itself have a sparse basis for its cycle space. And then we'll say, bingo, that can't be true. And we'll just, I mean, we could just do it by hand. Okay, so is the approach clear, what we have to do now? Right, so first thing we have to do is show that if we shed edges, if we delete an edge, then the property of the cycle space having a sparse basis is going to be maintained. Now, as an aside here, if you have a clever proof strategy in anything you want to prove, there's always one sanity check that you ought to perform, and that is, well, maybe in some roundabout way, what you're planning to prove is going to prove what you want to prove, but it might be too strong. So your clever plan might involve proving something that is far too strong, or maybe just too strong, to always hold, and then whether or not implies what you really desire, this is not a feasible way of proving it, because you might have an example where this stronger property fails, and yet what you want to prove is true. And for this example, you won't be able to prove it in this roundabout way. So it's always a good sanity check to check that if you prove a desired statement in some roundabout way, that then the interim steps are not going to be stronger than what you want. How do you check that? Well, if the theorem is true, then if you can prove that the interim statement follows, then you're in good shape. Then you're not trying to prove something that is too strong, because if you had any old proof of the direct implication, then this interim statement would follow from that. So you're not aiming too high in aiming for that. And now, the interim statement we want to show is that if we delete edges, then the property of the cycle space having a sparse basis is going to be maintained. Now, in our case, what we want to show is that our given graph, the graph we're talking about which we want to prove that, should at the end of the day be planar. right? If the cycle space has a sparse basis, then we want to show it's planar. Well, if it is planar, planarity is closed under deleting edges, right? So we're not going to prove too much by trying that. Okay, so let's start and consider an edge, little e. First case, this little e we want to show that the cycle space of G minus this little e has a sparse basis if G did. Okay, and we're going to consider a case distinction. The first case is that this little e lies in only one element of our basis that we have for the cycle space of G, say in the first one, C1. Okay. If that is the case, then I claim that we can generate the cycle space of G minus E from the other cycles. Why? Well, C1 contains this little e. We can't use C1 in any linear combination of our given cycle space element because we'll be unable to get rid of this edge e by any linear combination of C2 to whatever, CK. Right? So if we linearly combine it in G, and we know that little e is in C1 and not in any other of the basis elements, then if our given cycle doesn't contain E, then our linear combination will not involve C1. So we combine it from the other elements of the basis that we have for G, for the cycle space of G, and then we'll be done. There's a slight snag here in what I said. Look, I hope it sounds convincing, but there's a little property that where you would probably have pricked up your ears and said, oh, well, is that right? Did anyone catch it? Yeah?
I can't build an example where the edge is actually only part of the
Okay. So, but that's fine. So if you can't think of an example where this actually occurs, there's nothing wrong with proving it. No, there's another point. I said we want to generate the cycle space of G minus E. And I then talked about how we generated this set of edges in this, from the basis of the cycle space of G and so on. But can we do that? So I'm using implicitly that our given element of the cycle space of G minus E can be generated from this basis that we have for the cycle space of G. And then we'd better check that the cycle space of G minus E is a subset, is a subspace of the cycle space of G, so that our given element is indeed in the cycle space of G as well, so that we can start trying to generate it. And is it? Well, yes, it is, because the definition of the cycle space is whatever is generated from the cycles in the graph. And if you apply that to G minus E, then the cycles in G minus E are obviously also cycles in G. So what you can generate from them is certainly in the cycle space of G as well. Okay, so that was the case that our given edge that we want to delete lies in only one of the basis elements for the cycle space of G. Right, next case is that it lies in two of them, say C1 and C2. Right, it can't lie in more because our basis is sparse. Okay, if it lies in C1 and C2, then I claim that we get a basis for the cycle space of G minus E by taking C1 plus C2, the two basis elements for the cycle space of G that little e lies in, C1 plus C2, and all the other cycle space elements from that basis. Okay, so let's check that they generate, that they're linearly independent, and therefore form a basis of the cycle space of G minus E. Well, are they linearly independent? Yes. The answer is correct. If they were not linearly independent, then a sum of a subset of those elements, namely C1 plus C2 plus C3 and so on up to CK, a subset of those elements would sum to 0, but then also a subset of the original bases for G would sum to 0, namely C1, C2, and with the same coefficient as we have now, and then all the other C's. Right, so clearly they're linearly independent. Why do they generate? The cycle space of G minus E. Well, if we generated over G, and here we need the same little argument as before, that we must be able to do that because the cycle space of G minus E is a subspace of the cycle space of G, but we had that before. So if we generate it over G, then we can't use C1 without also using C2, because C1 will contribute our edge E. E lies in C1. And it also lies in C2 and not in any of the others, because it lies in at most 2. So if we use C1, we also have to use C2. And similarly, if we use C2, we also have to use C1, combining over in the cycle space of G. So we always use C1 and C2 together, or not at all. And that amounts to saying that we're using this new element, C1 plus C2, or we don't use it. Okay, and then is it sparse? Yes. Yes, it is, right? Because no edge can lie in C1 plus C2 and any of the other C's. Why not? Well, if it lies in C1 plus C2, it lies in exactly one of them. Otherwise, it wouldn't lie in this sum. And then, say it lies in C1, and then it can lie in at most one of the other C's, because the basis for the cycle space of G, or the C's, is sparse. Right. Questions? No? Okay. So let's move on to the next step. We have now shown that the property of having a sparse basis for the cycle space is preserved by deleting edges. So if our given graph, whose cycle space has a sparse basis, is not planar, as we want to show it is, then we can delete edges and arrive at a subdivided K5 or K3. Okay, so then this TK5, say, also has a sparse basis, and let's try and show that it doesn't. A sparse subset of the edge space is sparse, or the fact that it's sparse has an implication, has a consequence, and that is that its union consists of many edges, given its size. Right? If the elements of a set of subsets of the edge set is sparse, and every edge lies in at most 2 of them, then these certain number of edge sets in their union cover lots of edges, because no edge lies in many of them. Okay? Okay, the size of these subsets also plays into that calculation, of course. But maybe we can already prove that K5 cannot have a sparse basis because a basis would have so many elements that throwing in sparse means that the union of the edge sets of these basis elements are more edges than K5 contains. You getting the idea? Right. So let's try and do that calculation. The dimension of the cycle space of K5 is, well, what is it? Well, we had this basis consisting of fundamental cycles, so the graph is connected. That's number of edges minus number of vertices plus 1. And what's that? Well, number of edges of K5 is 10. Number of vertices is 5. 10 minus 5 is 5, plus 1 is 6. So every element of this cycle space that we use there contributes a number of edges. How many? Well, it's an element of the cycle space, and therefore a disjoint union of cycles. So at least 3 elements. Right? So all the elements together contributed by this sparse space, this hypothetical sparse spaces of K5, all these elements together, there are 6 elements, and each of them throws in 3 edges. So we get 18 edges. All right? How many? Every edge there gets counted at most twice. So perhaps it does get counted twice. And then we have overcounted only by a factor of 2. So the 18 edges that we counted imply that K5 has at least 9 edges. And now we want to try contradiction. And we have a little feat to perform still in order to be able to do that, and that is we have to prove that 9 is bigger than 10, which I can't do today without my notes. So that failed. Okay, so here's a little trick that enables us to do that all the same. So let's consider this bases, 6 elements, C1 to C6, and then add one more, and that is the sum of all those, C1 plus C6. Right? That's no longer a basis, that's linearly dependent, but it's still sparse. Right? Because any edge that lies in this sum will lie in exactly one of these elements. Well, it can't lie in more than 2 because this is sparse. It can't lie in exactly 2 because then it wouldn't lie in this sum. So it lies in exactly 1. But then that's fine. That lives up to the definition of being sparse. So that's a sparse set. Right, and now we can do the same calculation as before, but not with 6, but with 7. We have a sparse set of 7 elements of the cycle space. And so Now there are 7 times at least 3 edges that each of them contributes. So we get to at least 21. Bingo. Right? And 21 is bigger than 20, or 21 over 2 is bigger than the number of edges of K5, which is 10. Right, so we do have a contradiction here, and the proof for K33, which we still have to do, is exactly the same, except that we have to use there in the calculation that all the cycles, all the cycle space elements contribute at least 4 edges, because K33 doesn't have a triangle, and we actually need this 4 rather than 3 to make the sums work. But that's it. Okay, so we have proved MacLane's theorem, and now as a corollary, we get this characterization of planarity that I promised you at the start of this lecture. And now we rephrase phase boundary in terms of peripheral cycles, and the theorem says that a graph, a free-connected graph, is planar if and only if every edge lies on at most 2 peripheral cycles. That's called Tutte's planarity criterion. It was proved by Sascha Kelmans in 1978, I believe independently of Tutte and a little earlier. So I attribute it to Kelmans, but it's known as Tutte's planarity criterion. Right, so why is that true? Well, the forward implication is clear again. If the graph is planar, it has a drawing, and the phase boundaries of this drawing is sparse, form a sparse set of cycles, and they are the peripheral cycles of this graph. So every edge lies on at most 2 peripheral cycles. And the other implication is now also easy, right? So if we have a graph, a 3-connected graph, where every edge lies on at most 2 peripheral cycles, well, these peripheral cycles, as we showed last time, they generate its cycle space. Right? And here we need 3 connected. And under that assumption, we prove that the peripheral cycles, planarity and art, the peripheral cycles of the 3-connected graph generate its cycle space. But now our assumption is that every edge lies on at most 2 of those things. So this generating set is sparse. And then it contains a basis that is still sparse. So it has a sparse basis, but by MacLane's theorem, the graph is planar. Okay? Good. Right, so that was the first topic of today, and now I want to go back to cycles and cuts. Right, so the cycles and cuts in a graph are mysteriously, or not, I think mysteriously, related to each other. We had a few examples already. The orthogonal space to one of them is the other, right? The space, the subspace of the edge space that's orthogonal to the cycle space is precisely the cut space, and the other way around as well. The dimensions add up to the dimension of the edge space, even though these spaces can overlap non-trivially. We had this duality condition that is on the exercise sheet as a minus exercise, saying that given any spanning tree, a non-tree edge, little e, lies in the fundamental cut belonging to a tree edge f, if and only if this f lies in the fundamental cycle belonging to this e, right? E is in df if and only if f is in ce, this duality condition. And then we had that the cycle space is the kernel of the incidence matrix B, or of the boundary map, and the cut space is the image of its transpose, the co-boundary map. So cycle and cut spaces do hang together in all sorts of ways, and so one can ask a question that would be outrageous to ask if that wasn't the case. And the question is the following. Let's talk about multigraphs for the moment. And the reason is not so much that I want lots of parallel edges and loops. The reason is that I want to use the definition that we have for multigraphs, where rather than our graph definitions where we start with a set of vertices and then we say edges are two sets of these vertices, we now have two sets, a set of vertices and a set of edges, and then we have some incidence maps, right? So that's the formal definition of a multigraph that we use, and part or a consequence of that definition is that it's meaningful to ask whether a certain set can be the edge set of two graphs. In principle, it can be, because it's just a set, and then you have, for two sets of vertices that have nothing to do with each other, a different pair of incidences from this one set of edges. Okay, and now here's the question. Is it possible, if we have a graph, or is it conceivable ever for any example, that we have a graph and it has certain cycles, they generate a certain cycle space? Is it possible to have another graph? Sorry, I always mean multigraph now, but I'll continue to say graph, meaning multigraph. So can we have another graph where these same subsets of the edges that are elements of the cycle space of our given graph G, certain sets of edges, precisely those sets of edges in the other graph are precisely its cuts? Outrageous. I mean, how should that possibly be true for any graph? So equivalently, the cycles in the given graph, the edge sets of cycles, should be precisely the bonds in that other graph. We have one set of edges. We want to sprinkle them over some set of vertices here. Look which subsets of the edge set make cycles. Then we say, okay, I'll remember those as abstract separate sets of edges. And then I look how they sit in the other graph, and I want the answer that those are precisely the bonds. Okay, and we're going to see that not only is that possible, but there's a very, very simple characterization of the graphs that make this possible, of the G's for which there exists such another graph. And which graphs do you think allow that? The answer is, it's exactly the planar graphs. Isn't that weird? Okay? So for exactly the planar graphs is this possible, to find another graph whose bonds are precisely its cycles. And this is known as Whitney's planarity criterion, right? A graph is planar if and only if there exists another graph whose bonds are precisely its cycles, always with the same edge set. And always graph means multigraph today, or from now on. That's thought of normally as a planarity criterion. It tells us something that plane graphs or planar graphs do satisfy, and we can show that. That's not too hard. and then the interesting thing is the converse. I was talking to, many years ago, I was talking to Jack Edmonds. Jack Edmonds, must be 90 or something now, is one of the early champions of matroid theory, and he's also an optimizer, is famous in combinatorial optimization for all sorts of things. So Jack Edmonds is a real character, and I was on a walk with him, and we got to talk about this theorem, Whitney's theorem, and I refer to it as a planarity criterion. He said, it's not a planarity criterion, it doesn't characterize planarity. I said, well, does it not? What then does it characterize? He said, well, it characterizes those graphs that have this incredible property that I tried to sell to you earlier. And that, he said, was the outrageous property, and that, of course, did come from matroids, but then matroids came from planar graphs, so it's all modeled up with each other. But anyway, whichever way you see it, the implication is interesting both ways, right? For every planar graph, is it possible to lift off its edges, put them on some other set of vertices in some other way so that the cycles become precisely the bonds. That's true for planar graphs, that's interesting. The other direction, is it ever possible to have this lifting and transfer property? Can't really be true anywhere. Yes, it is true, and it's true precisely for the planar graphs. That is also interesting. Okay, so wonderful theorem. And those graphs, these other graphs that satisfy that, we shall call the abstract duals of the given graphs, G. Okay, so we have a graph G with a certain set of edges. There it is. And then there's another graph with this property that I mentioned, and we call that G star and call it a dual of this G. Now, okay, so you probably learned to your great surprise in year one that in mathematics we're allowed to make any definitions that we like, and we can use any words that we like for whatever property we want to find a word for. In principle, that's true. I mean, like all things at university, it's true in as far as it imposes a demand on you, the students. Right? You are not allowed to say, yes, but basis means something else. It means that it's fundamental and I can sit on it and so on. No, it means what we defined. So you have to take that bitter pill, and you're not allowed to appeal to your intuition or to your previous knowledge or associate a word with something else you've heard of, as people in the arts do all the time, philosophers do all the time, and then argue over what something means. No, it means what it's defined to mean. Right. So that's one thing you learn. Then when you grow up and you begin to do your own mathematics, and then you come up with some structures that you want names for, then suddenly this is no longer true. You are not allowed to choose any old word for whatever you have just invented. And that's sometimes a hard lesson to learn. For example, you can't use dual without it meriting being called a dual. And one of these things that a dual ought to satisfy, one of many things, is that if you take the dual again, you should get the original back. You shouldn't call something a dual that doesn't satisfy that. Okay, so is that the case? If we apply this process to the graph that we have found, do we get this back? Right, what do we have to show? Well, we would have to show that the cut space of the original graph, which is going to be the other graph for that other graph. So the cut space of G should be the cycle space of that other graph. So we ought to at least satisfy that in order to be allowed to use the word dual. Well, but that's not so difficult, because the cut space of G is the cycle space of G orthogonal. And now we can use the definition of this other graph G star, namely that its cut space is the cycle space of G. So this is the cut space of G star orthogonal. And all we need now is that these two are equal. But yes, they are. As we have shown for any graph, its cut space is the orthogonal space to its cycle space. So this minimum requirement for permission to use the word dual for G and G star, or G and G star, at least is satisfied. Right, so we can also write G double star is G. Can we write that? Well, not quite yet, because what is G double star? It's finding another graph for G star, but which other graph? And what is G star? I have never told you that. I've never told you, here's your graph G, and now we define a graph G star in this or that way, and then it satisfies this edge transfer stuff. We just said if there are two graphs, and the second satisfies this edge transfer stuff, then we call that a dual of this. Okay, so we need a little more, and we need that this other graph, G star, is unique and then we can talk about it and apply star to it again to get G double star, and that's a well-defined graph if this uniqueness is true for all these graphs G and G star, and then we can ask, are we getting G back? And the answer is yes, we are. And that is true if G is free connected. Well, we need that, otherwise it's not true. I believe there's going to be an exercise about that as well. And then there's lots of elementary stuff going on there. It's not interesting just by that, believe that we need G star to be, G to be free connected, then G star is also going to be free connected. And any G star that we get in this way, and there is only one. We get that G star is uniquely determined. Right. Now, one little observation. The edge sets of the blocks of G, they live as some sets up there in the common edge space or edge set. The edge sets of the blocks here are precisely the edge sets of the blocks of G star. Why? Well, we proved that. We proved that lying in a two-connected graph, let's look at blocks, two connected blocks, you can also look at bridges, but let's look at two connected blocks. We proved that lying on a common cycle is the same as lying in the same block. And lying on a common bond is also the same as lying in a common block. And the corollary of that was that lying on the same cycle is an equivalence relation. Lying in a common bond is also an equivalence relation because lying in a common block clearly is an equivalence relation. Okay, so if we look at the blocks of G, then that's an equivalence class with respect to these three versions of the same equivalence relation. And belonging to the same cycle is the same as belonging to the same bond in G star. So these equivalence classes are the blocks here, and also the cycles, the classes for the equivalence relation of lying on a common cycle. And that's the equivalence relation of lying in a common bond in G star. And those equivalence classes are also the blocks of G star. So these are in fact the same. Okay, so that's nice to know. And as a consequence, we see that the cycles and the bonds of G star or G are precisely those cycles or bonds of their blocks. Right? We proved that as well, that a cycle in a graph always lies in a block, and a cycle in a block obviously is also a cycle in the graph, and we proved the same for bonds. Not only are the sets of edges of the blocks the same in G as they are in G star, but also if you take such a block as a graph and you form its dual, then that's going to be a block of the dual G star. Okay, so let's turn to Whitney's theorem. And in order to do that, we need to define not abstract, but topological duality, plane duality, as we shall call it, in plane graphs. And the idea, of course, is that abstract duality for graphs that happen to be planar or will, in any drawing, then produce this plane duality. But of course, historically, it's the other way around, that we had plane graphs first and observed an obvious duality there, and then abstracted from that to get this edge transfer property, which we call abstract duality now. Okay, so given two graphs, two plane graphs now, here's the idea. We start with one plane graph. Okay, so here we are, that's a plane graph. And then the idea is to form another graph by taking as the vertices of this other graph the faces of the given graph. It's going to be my new graph, the outer face as well. Right? And then faces that are adjacent in the sense that their edge boundaries share an edge are made adjacent as vertices of that new graph. life experience proves that I've forgotten something, but I can't see what I've forgotten, so don't worry about it. And if I have, then just put it in. That's the idea. But have I now defined this blue graph? Well, I sort of defined it as an abstract graph. I told you what the vertex set is. I told you when two vertices are adjacent. But I got from a plane graph something that is not a plane graph, but an abstract graph. And still we could try to prove now that this new abstract graph is an abstract dual of the plane graph that we started with when we consider it as an abstract graph. So we could try to prove that the bonds of the blue graph are precisely the cycles of the white graph that we started with. And if we look at a cycle, yeah, sort of this face boundary is a bond in blue. Ah, I found one edge that I forgot. See, life experience doesn't cheat. There we go. Right, so that's the bond that consists of all the edges at this vertex of T star. But we could also take a bigger cycle. And then if we look at the blue edges that cross the white edges on that cycle, which have now turned orange, then this set of blue edges is a bond in the blue graph. Why? Well, these blue edges that go out of this plane cycle, the orange cycle, they separate the inside from the outside. More precisely, they separate the blue dots that are inside the orange cycle from those blue dots that are outside the blonde cycle. And they do that minimally because if I left one of them out, then topologically I could get from this bond here to a node here from this blue vertex through that gap here to any other one. So the remaining blue edges, those that cross all but one of the orange edges, would not separate those two blue vertices anymore. Okay, so it looks like we're in good shape for the blue graph to be an abstract dual of the white graph. But let's define duality for plane graphs, two plane graphs. And I haven't defined a blue plane graph. I have drawn one, but I haven't told you exactly where to put this vertex, at which point in the plane to put this vertex. I told you to put it inside the face, this face, but not exactly where. I haven't told you how wiggly these blue edges are and where exactly they run and so on. I haven't given you a plane graph. So let's start with two plane graphs, and just assert when they are going to be called dual to each other. Now, both are given. The white graph is given, the blue graph is given, and if they satisfy certain things, then we shall call them dual, topologically dual to each other. And what are the certain things? Well, they are the obvious things that you would want. So from the set of faces of the white graph, for every face we want to draw a new vertex. And if the face is called little f, then this is going to be v star of f. From the edges of the white graph, we want to get edges of the blue graph. Well, namely, I said if two faces are adjacent in the sense of sharing an edge, then I throw in a blue edge to join the vertices corresponding to those two faces. And the way I drew that here is precisely I drew this new blue edge across that white edge that lay on the face boundaries of those two faces, on the boundaries of those two faces. So we get a map that assigns to every edge of of G a blue edge E star. And then we also want from the vertices of G to get faces of the blue graph, so that if you start with a little vertex V, then you get a face which I shall call F star of this little V in the blue graph. And we want those maps to be bijections, right? For every white face, you get exactly one vertex, one blue vertex. For every white edge, you get exactly one blue edge. And then we want the same thing dually. Well, I wrote it up in this way. I wrote up the definition in this perfectly symmetrical way in order for it to be symmetric. G and G star should satisfy something, if should be called dual, topologically dual, if certain things hold. And what I'm asking them to hold should be symmetrical in G and G star. Right? So if I want this to exist as a bijection, then I have to ask this as well in order to make it symmetrical. Okay, but that's fine. And then we don't just want any bijections like there, but we want particular ones. So the blue vertices here should lie in the face to which they belong. That's condition one there. Every V star of F lies in that F, in the plane. The edges E star, they should meet the entire plane graph G only in one point. And that one point should be an inner point of the edge E. And then for symmetry, we want the converse as well. So these meeting points should also be an inner points of the edges E star. And then to make our calculations easier, since we're piecewise linear in our drawings, as always, we want these points in the inner points of E and the inner point of E star to be, in fact, in the interior of one of these straight line segments. But that's just to make life easier. For doing pedestrian proofs, which luckily you're not going to have to do this time, graph theory 1, planarity is full of these terrible pedestrian proofs which turn out to be so hard, but they're really boring, and now we can use them all, right? So we don't have to do that, but maybe that's a reminder for those of you that have sat in this course, graph theory 1, here in Hamburg. Okay, so that's the definition of duality, of plane duality, or topological duality for plane graphs. Questions about that definition? No? Okay. So, I'm going to lie to you, as I sometimes do, but I'm not going to tell you when. So I'll give you a few properties now, and maybe you can try to find this space, the place where I lie to you. Let's see. So first, the first elementary thing, obviously, we want is that these blue graphs exist. And I showed you, well, I nearly showed you how they exist, or why they exist. So if we start with a white graph again, then we have to define now, topologically, or show that a blue graph exists that satisfies all these things, right? So we pick for every face, little f, of the white graph, we pick a point in that face, in the interior of that face, and we call that point V star of that little f. Just pick one. I'm not going to define precisely, given any plane graph G, what G star is going to be. I'm going to prove to you that G star exists, that some plane graph exists that satisfies as G star all these properties together with G. So, and for the existence, I'll just say, well, pick any point from inside a face and call it V star of that face. Now, next we need edges. Well, also easy. For every edge of the graph, we start, white edge, we start drawing E star by a tiny little segment across an inner segment of E. So this is E, and this is the beginning of E star. And then once we're in that face, through this little bridge, we find our way in a polygonal arc to that vertex in there, the blue vertex that is already there. And here the same, like this. Okay, can we do that? Yes, we can. So if we do it for this edge afterwards, say we make our little bridge here, then we connect this here, and we try to connect this to there, and as we go there, we suddenly get to another blue edge that we've drawn before, but never mind, we'll just follow it. Follow it round, and then we get to that point. Okay, this is the kind of elementary topology that you don't have to do this in a master's, but that's certainly possible. Okay, and that's how this graph is defined, how one can define a blue graph G star. And then obviously we have to prove that this will hold as well, that for every vertex of G, there is a face of the blue graph, G star, in which it lies. And that's easy, because we just, V has some white edges that are incident with it. All these have little blue bridges already. And then we just follow the bridge to the vertex, then go back to this, and so on. And then we get a face in the blue star. That's also elementary. Okay. So this blue graph G star is obviously not unique as a plane graph, but it is unique as an abstract graph. Well, that is really, really weak. Every other plane graph satisfying these conditions as G star together with G is isomorphic to this one. Yes, isomorphic is very, very weak. It just means there exists a bijection between the vertex sets that preserves adjacency and non-adjacency. Well, there's a particular bijection if we have another candidate, then from its vertices, we can find an f of g that it came from. And our original blue graph also has a vertex that lies in that f. So I would map these vertices to each other, and then we would do the same for the edges. The blue edges in the first dual, topological dual, and those correspond to dark blue edges in the other dual, and then I would map these two dual edges to each other, and then I want that this map is in fact a graph isomorphism, and the reason for that is that the vertex, a dual vertex is incident with an edge, a dual edge. A dual vertex is incident with a dual edge if and only if the face that it lies in, the face of G, has the corresponding edge of E in its boundary. And that is true for both candidates for our dual G star. And since that is true for both of them, the incidences are compatible with these bijections between their vertex sets and the edge sets that I defined for you just a moment ago. So all this is elementary. I encourage you to do it sort of at home, fill in the details until you think, yeah, I can do that. Be honest to yourself, but then don't write it down, right? It's the kind of thing that is easy to believe and to be persuaded of while being false, and you should be sure enough that it's not false. But that's how it works. So the assertion is that G star is in fact unique up to isomorphism of graphs, not only any isomorphism, but isomorphisms that commute with this. Okay, something even stronger is true. If you have another blue graph, another G star, there is an isomorphism from the old blue G star to that one that is induced by a homeomorphism of the sphere. So if you think of both of them as embedded in the sphere rather than the plane, you can you can move the entire sphere. You can even ask for G to be fixed in this movement, so that you just move the inside of this. You keep this edge fixed, and then you move the inside of a face so as to get one blue dot on top of the other blue dot, and one plane edge, a polygonal arc on top of the other polygonal arc, and so on. So you can prove that there is even an isomorphism that comes between the graphs that is induced by a homeomorphism of the sphere like that. And that's also elementary, also tedious, and also something you don't have to do. The fact that G star is unique in this pretty strong sense is something that you ought to remember. Okay, and then, since it's unique, we have the same as earlier. We can check whether G double star is G again, up to this little bit of fiddling. But now this is meaningful to state. And this is true and witnessed by these three maps that we have here. Right, so and since they're bijections, the inverse maps, the maps and the inverse maps give you from G, you go to G star, and then you go back to G, and you end up where you started from. Okay. And now comes the point of waking up. You can give me your long list of mistakes that are made on the way in a moment, but I'll alert you to one thing that is really suspicious. Now, the observation is that the blue graphs are clearly connected. Why are they clearly connected? Well, if the white graph G is disconnected here, you have a little bit of white graph, and here you have a little bit of white graph, and then there's the sea in which they swim. The blue graph is going to be connected from any blue vertex. You can get to any blue vertex by an arc in the plane. And if that arc happens to hit a vertex, okay, go around that vertex so that you only hit an edge. If you go back and forth between this edge, don't do that. Just go along the edge and then so that you hit it only once. So that's easy. Between any point in the plane that is not on the white graph G, and which is, for example, a blue vertex, and any other such point, you can find an arc in the plane that hits G in such a way that it crosses, that it hits it only in edges. In these edges, it hits it only in inner points of straight line segments, and it hits every edge only once, at most once. So that is easy topology. So blue graphs are connected. G star is connected. Okay? So this graph star is connected. So I've just proved that G is connected. Brilliant. All right, we started out with this graph G, clearly disconnected. Here's a little bit of G, and there's a little bit of G, and then we proved that it's connected, in fact. I can't be right. What's wrong? No, it'd be too much to ask that you should have noticed the error. It's a very well hidden error. And it lies in the fact that if G is not connected, then, well, something must go wrong in the reasoning that I gave you. And what goes wrong is that this map here, is not going to be injective. All right? So the others clearly are. These are clearly bijections. That maybe is not. And here's an example. So let's take a disconnected G. What's the blue? What is a blue graph? Well, there's only one face, so I draw only one blue vertex. And then for every edge of G, I'll make my little bridge, and then I go to that vertex. So that's G star. G star is indeed connected. Right? But this map here maps both these vertices to the same face of the blue graph, namely this outer face. Okay, so something had to be wrong, and then one just has to go through everything and see exactly what is true and what isn't true. And that's why these things that can go wrong are so useful, because one of these very non-trivial abilities you ought to acquire in this course of study is to be able to tell correct reasoning from a rumor. So to follow through an argument and see exactly what is true and what isn't true. And it's quite amazing how different are the standards between mathematicians and the rest of the population in that respect. So that's how you are likely to earn your money in the future, by finding which statements that you are presented with are in fact true and which are maybe only likely true. Okay, so mathematics is a good playground to practice that because there can't be any disagreement, and especially when you find a counterexample like this to a statement that you believed was correct, then that's fine. So, except for Julia, I think nobody was in my, no, maybe, Kai, were you in my linear algebra? No, okay. So maybe none of you was. So early on in my first year course, I asked the students, what do you think is a mathematical proof? And and they come up with lots of things like logic and deduction from axioms and blah, all sorts of things they've heard. And then my suggestion of what is a mathematical proof is the following. A proof is when, that's a good start, a proof is when sufficiently many, sufficiently trained, sufficiently serious, sufficiently honest mathematicians think about it for sufficiently long and then come back and say, that's a proof. Right? So there is no, I mean, one can make this definition a little more precise, and that then is indeed going to be logic. But the lesson is that in practice, we can never be sure. We just go through the arguments and try and ask ourselves really, really honestly if we see anything missing, if we see a mistake, but also if we see an omission. And if we can't see those, then we do it again, and then if that feeling doesn't leave us, then sometimes the feeling of, yeah, is probably okay, I don't think I've missed anything, sort of metamorphoses into something, yes, no, I now know it's true. That can be false. I've had it done to me that it was false, that I believed something was absolutely watertight and it wasn't true. But it helps. This feeling will, with training, arise in you more and more in the correct instances. But yeah, so that's basically all you can do. And you can never be sure. It's amazing, though, that we all agree. So if one mathematician says that's a correct proof and the other says, no, that isn't a correct proof, or it doesn't persuade me, then if the two sit down together, or even if they sit down individually and think for long enough, it's almost always the case, or it is in fact always the case, that they come up with a joint solution at the end of the day. I mean, sometimes there exist proofs that are so sketchy and so complicated that some experts say, yeah, this is obvious, and others say, no, it isn't. Then those that say it's obvious have to come up with what they think is a pedestrian proof of that obvious statement, but they can. So it just doesn't happen. We don't have schools in mathematics where one school claims that this statement is the correct theorem and the other says, no, that's false, and that we don't have that. And that is a statement that doesn't have to be true. That's amazing, because from the way that I defined proof, this doesn't follow. It doesn't have to be the case, but it is the case. So that's interesting. Okay, sorry, end of storytelling. Where are we? I want to show you a little, sorry, yes. The remedy is that we need, for the existence of G star, we need that G is connected, right? And then it does work. Okay, so proposition, if we look at G and G star, any dual G star, so if G is not 3 connected, it need be unique, then the cycles in G are precisely the bonds of G star. So if they're topological plane duals, then they are also abstract duals as we defined those. Why is that so? So if you take a cycle in G, it's a certain set of edges, then here the orange cycle, then the blue edges that cross those form a bond. They separate the vertices on the inside, and there's at least one, because if this is a face, this contains a face, either it is a face or not, contains a face, in that face we put a blue vertex. So the blue vertices here from the blue vertices outside, and that's also a face. Maybe the same face, no, not for a cycle. And so there are blue vertices inside, blue vertices outside, and the blue edges that cross white edges do separate the former from the latter. So they do form a cut, and the sides of that cut are connected. Same reason as before, from any point not in G inside this face of orange, I can walk to any other in the plane and without hitting orange, and that's Jordan curve theorem. So I can walk along blue edges from any blue vertex inside orange to any other blue vertex inside orange by adapting such an arc to walk along the blue edges as I wish. So if we have an edge set in G, that's a cycle, then the corresponding blue edges form a cut with connected sides, and a cut with connected sides is a bond. Remember? Okay, so a set of cycles, a cycle in G is going to be a bond in G star, and the other way around. If we start with a bond in G star, well, some set of edges, there's a bipartition of the blue vertices, and it's all the edges across. These are even connected. Why do these blue edges, if we turn them into white edges, form a cycle? Well, they contain a cycle. Let's start with that. The white edges corresponding to the cut edges of blue contain a cycle, because if they didn't, then white would be acyclic. It would be a forest. Right? But if you take a white forest and form its dual, then that has only one face. Right? So blue has only one vertex. And so we can't have a bipartition, as we do in fact have when we start out with a cut or even a bond. Okay, so the white edges corresponding to the blue bond contain a cycle, and then by minimality they in fact are a cycle, because if they had a proper subset that was still a cycle, then as we just saw, this proper subset, the white cycle, would correspond to a blue cut properly contained in the given blue cut that we started with. And then the given blue cut wouldn't have been a bond contradiction. Okay, so the plane duals do what they ought to do. They are abstract duals as well. Okay, so back to Whitney. Here's Whitney's theorem. If you have a connected graph G, and now connected is important, then it has an abstract dual, namely take any topological dual, and that's an abstract dual, as we just saw. But also conversely, if you have a connected graph, and you know that it has an abstract dual, then its cycle space is the cut space of some other graph. Now we want our graph to be planar, right? That's the backwards direction, backwards implication of Whitney's theorem. If G has an abstract dual, G star, we want to prove it's planar. Well, if it has an abstract dual, that means that its cycle space is the cut space of some other graph, namely of the dual. That's the definition of abstract duality. So I want it to be planar. And the reason is MacLane's theorem. Right? It has the cycle space. We want the cycle space to have a sparse basis. Well, the cut space has of G star has a sparse basis. Namely, well, ideally it should be what the plane case tells us, but now we don't know that the graph is planar. Does the cut space always have a sparse basis? Yes, it does. The atomic cuts, remember them? One vertex, all the incident edges. They generate the cut space and therefore contain a basis. So the cut space of the dual has a sparse basis. Now, those elements of the cut space in that basis, they exist in this other graph, and here there are elements of the cycle space. So the cycle space has a sparse basis because sparsity is the same. It just means every edge, and they're the same, it just common edge set. Every edge lies in most two elements. Okay, so the cycle space has a sparse basis, and then by MacLane's theorem, the graph is planar.